Okay, I think it's 2 o'clock, so in the interest of time, I'm going to get started. So hello and welcome to the Annual Beckman-Brown Lecture on Interdisciplinary Science. I'm Diane Beck, Interim Head of the Department of Psychology and a member of the Beckman Institute Executive Committee. I was given the privilege of introducing today's speaker, Dr. Fei-Fei Li, because she's been a longtime collaborator and friend, and that was a collaboration and friendship that started here at the Beckman Institute. But first, a little about the lecture series. The lecture honors the late Arnold O. Beckman, the founder of the Institute, and Dr. Ted Brown, the founding director, who, I'm pleased to say, is with us today. The Arnold and Mabel Beckman Foundation has endowed this lecture series, and we continue to be exceedingly grateful for its support. And before I introduce today's speaker, I'd like to ask Ted to say a few words. Ted?
Thank you, Dan. I really appreciate the opportunity to be with you today for this lecture, and I'm looking forward to a fascinating talk. I want to say a few words to remind us all of what we owe Arnold and Mabel Beckman for the existence of this building, not this virtual building, but that real building in which everything takes place, and the environment there. And through the support over the years from the foundation, the Arnold and Mabel Beckman Foundation, for our programs, we have been so fortunate to have the support of the foundation in so many ways. Arnold and Mabel were wonderful people. They were very dear friends of mine, and I miss them a lot. Several years ago, the Beckman Foundation made an endowment gift to the University of Illinois to support this annual lectureship in interdisciplinary science and also a postdoctoral fellowship in interdisciplinary science. This year, the Institute will have a new postdoctoral fellow coming in to here, and her name is let me find my word. The other one is Ayman Ahmed, and she will be working with Martha Gillette and Brad Sutton. Now, I just want to say something about this subject today. When the Institute opened its doors in 1989, we had a group here called Cognitive Sciences. And it had been formed from a multitude of disciplines and so forth. And we were very happy. I was very happy to have them coming into the Beckman Institute. But it was just beginning to be something that was recognized as a significant discipline in its own right. And in fact, it was only 2 years after the Institute opened up in 1991, this book by Bddl and Thompson and Roche came out, called The Embodied Mind, and it was exemplary of the notion of how much our mind is embodied and how much it interacts with the world around us. And so we've had a proliferation of wonderful science in those years ever since then, at the Beckman Institute and other places. And today's lecture is certainly an example of the extent of the reach of this idea, of this concept of embodiment and our connection with the world through, in this case, artificial intelligence. So I'll turn it over again, Diane, to you to introduce our speaker. Thank you.
Thank you, Ted. So the Beckman Institute is all about bringing together people to cross disciplines and break barriers. And this is why I'm so pleased to welcome Fei-Fei Li, the Sequoia Professor of Computer Science at Stanford University and the Denning co-director of the Stanford Institute of Human-Centered AI. Fei-Fei is one of those rare individuals who not only does boundary crossing work, but has also substantively contributed to 2 disparate fields, computer science and human neuroscience. Her research includes cognitively inspired AI, machine learning, deep learning, computer vision, and AI for healthcare. Before co-founding Human-Centered AI, she serves as director of Stanford's AI Lab. During a sabbatical from Stanford in 2017 through 2018, Fei-Fei was a vice president at Google and chief scientist of AI ML at Google Cloud. She serves on the National AI Research Task Force commissioned by Congress and White House, and is an elected member of the National Academy of Engineering the National Academy of Medicine, and the American Academy of Arts and Sciences. She's also co-founder and chairperson of the board of a national nonprofit called AI for All, focusing on training diverse K-12 students, K through 12 students of underprivileged communities to become tomorrow's AI leaders. Prior to joining Stanford, she was on the faculty at Princeton University and here at the University of Illinois, Urbana-Champaign, where she was an active member of Beckman Institute. It is for all these reasons that I'm pleased to introduce you to her today. So that Dr. Li may complete her talk uninterrupted, I ask that you submit your questions to the Beckman co-hosts through the chat. Then at the end of the talk, we will ask some of those questions, but also allow you to unmute yourself to ask the questions yourself if you so wish. So her talk is titled From Seeing to Doing, Understanding and Interacting with the Real World. Thanks for being here, Fei-Fei.
Thank you, Diane. Thank you, Ted. Can you guys hear me?
Yeah.
Okay, great, and see the slides.
Yes.
Yeah. Okay, great. Well, first of all, what an honor to be here. I was just saying that I wish this is not totally virtual. Beckman, I feel like I owe everything in my career to the beginning of Beckman Institute, because that's my first job. It was also on the second floor hallway that Diane and I met as two young assistant professors started a decade-long collaboration in our research. So really quite excited and honored to be here, and looking forward to having some discussions after this the presentation. So I'm just gonna dive right in. And please shout out if there's anything you're not seeing the slides or anything, because I don't see the other modes. Okay, so let me just transport you 540 million years ago, just for a moment. What does life look like at that time? It was more or less the primordial soup. Life is all in the ocean, and it was actually pretty chill. There aren't that many animal species. They're just floating around. And then something really puzzling happened in geologically a very short amount of time. It's about 10 million years. Fossil studies have told us that animal species just exploded, and zoologists call this the Cambrian Explosion, or the Big Bang of evolution. So what happened? What caused this was a real mystery. And there are many theories, from climate change to the chemical composition of the ocean and so on. But there's one important theory, leading theory, that sheds some light, pun intended, I guess, to the rest of this talk. And that is by Australian zoologist Andrew Parker. He used fossils studies to conjecture that the Cambrian explosion is triggered by the sudden evolution of vision, which set off an evolutionary arms race where animals either evolved or died. So vision was an essential part of the evolution of animal species, especially animal intelligence, of course, along with other sensory systems. Well, fast forward 40 years later, vision is one of the, if not the primary sensory systems that animals use to navigate and survive and do everything in the visual world. There are a few species that do not use vision primarily, but that's very far and sparse. And so my own research in the past 20 years has been a journey of studying vision, especially studying, getting inspired by human vision and trying to apply that to machines and making computers see. I'm passionate about this because I do believe vision is the cornerstone of intelligence. So if we have a dream of making AI and making intelligent machines, vision is a core part of that. the rest of the talk is organized under two major bullet points. What does vision do? Vision helps us to understand the world, and vision helps us to do things in the world. So let's just start with understanding. In fact, let's just take a moment to reflect on how incredible humans are visual animals. This is a study about decades ago by Rsvp Biderman. He even before PCs were available, he designed a very clever experiment to show that object recognition is quite fast and special in human visual system. In two different kind of trials, an object here, a target object, in this case, a bicycle, is either in a congruent image, like the one on the left, or in an incongruent image, the one on the right that's a little scrambled. From a pixel point of view, the bicycle is identical in two conditions, and identical both in appearance and location. But interestingly, humans, in a very short amount of time, can detect the bicycle incongruent picture on the left better than the bicycle in the incongruent picture. So it speaks an incredible ability for the human system to see both the forest and the tree, so to speak, and integrate information of the complex scene in the visual world in order to detect objects. A similar line of work that draws similar conclusion, but in different ways, is the Rsvp studies of using videos, rapidly changing frames, to ask humans to detect object. In this case, the target object also is a person, I suspect, other than Diane probably, no one has seen this video. And yet, if I ask you to detect a person in one of the frames, where each one is only presented for 100 milliseconds, most of you would have no problem in detecting the person, even though you have never seen it, you don't know what the person looked like, the gesture, the appearance, and so on. Okay, so another study that impacted my own career, actually, starting grad school time, is the first study that put a number on the speed of visual recognition by Simon Thorpe and his colleagues, where they used the EEG ERP method specifically to measure how fast humans can categorize animal pictures, those on the left, versus non-animal pictures. Long story short, the study shows that after 150 milliseconds, from the onset of the stimuli, a human brain shows a differential signal that distinguishes animal pictures from non-animal pictures. And these are extremely complex pictures, novel photos, and many kinds of animal species and distractors. And last but not the least, I want to show you one study, a cognitive science study I did in my last year as a grad student and beginning of my Beckman time, actually, was trying to just ask what humans can see in a glance of a scene. And here we sit human subject in front of the computer and flash photos at them. Each photo is masked by a wallpaper-looking pattern, and the photos were flashed in various time duration, but they're very, very short. And it's incredible how robust the human visual system is. The longest time a picture like this is put on the screen was 500 milliseconds. And that's half a second. But depending on how you pay them, I guess, they can write novels. And this is, the amount of information humans can process by seeing a picture for half a second is almost infinity. And even in just within one eye movement or one saccade, under 100 milliseconds, humans can see a lot. So this study and everything I've said, I've shown using these seminal studies underscore one important ability of visual intelligence. That is, seeing is for understanding. It's not just processing colors and shades, it's not just registering pixels. There's something intrinsic in understanding the meaning of the visual world. In fact, one important building block of that meaning is seeing objects. If you look at the result again, and I here highlighted with pink colors, is that humans are able to articulate the objects they see in a scene. So all this inspired me to get on this very important problem to try to solve it, and that is the problem of object recognition. Here's the formal question, right? How do we enable computers to recognize objects, any objects in the world, just like humans can effortlessly do? So in this case, this is a very cute animal called wombat, and humans, at least some humans, can put a label on it, and we want the computers to do it. You might think, well, that's kind of easy. Well, mathematically speaking, it's actually really hard because there are infinite number of wombats that one could render onto an image. Even the same wombat can come in different lighting, view, camera angle, occlusion, and so on. And categorically, there are many individual examples. So this question is actually not trivial at all. And it was an important North Star problem around 20 years ago, or a little more than 20 years ago, in the field of computer vision and AI. So how did computer scientists went about this? Actually, the history of object recognition is a little bit of a history of AI, or at least in recent decades. We started as a field with hand design models, thinking about conjecturing what made humans see objects, piecing together geometric shapes and their relationships. Models like geons, models like generalized cylinders. These are heroic early attempts of hand designing object recognition models, and they're very limited in their ability. Then the second wave, or the second attempt of this field, came when machine learning came about. At the turn of the century, machine learning became the lingua de franca of AI and computer vision community, and we start to build statistical models, not by hand designing the model itself, but by using hand designed features like textured patches of images, but let machine learning models learn its own parameters, whether it's a geometric shape or the distribution of these patches. Here you started to hear about support vector machines, BaseNet, bag of words models, conditional random fields, and or graphs. And it's actually a period of incredible vibrancy where machine learning, computer vision came together and started to really produce powerful models. Another thing happened around the turn of the century in addition to machine learning was data. Data happened because the internet happened. While internet and digital devices started to take off, the field of computer vision started to benefit from that. So researchers were able to put together data sets for training and benchmark for testing. And one of the most famous data set was Pascal VOC, where 20 object classes were chosen, most of them in England. So I guess beer bottles and cows and others. And the whole field was able to train on Pascal VOC and start to work on these 20 objects. And that was when my students and I, around year 2006, by the way, this whole benchmark testing was run for almost 7 years. But something did bother me, especially coming from reading papers by Biederman and Thorpe and so on, is that the real world is more than 20 objects or more than 100 objects. The real world was so much bigger. And if you take it further and think about psychologists like J.J. Gibson, who would say that, think about not what's in your head, but what your head is inside of, how big this world is. So what I call this approach, the ecological approach of perception, is really recognizing and respecting the scale and diversity of the real world. So it dawned on me, and it was actually a really important moment in my own career, that seeing is not just for understanding, seeing is for understanding of the real world. So with that recognition, we start to look at these traditional data sets of object recognition in a more, a little bit of a negative light. It's not big enough. They're looking at 20 objects or, a few dozen objects. And that's when my student and I created ImageNet, where we are just going to go ballistic on respecting the scale of the world, the internet world we can get to, and created a data set of 15 million images across 22,000 object classes. And you're very familiar with this history. We put together ImageNet Object Recognition Challenge in 2012, 10 years ago. The winning entry was Jeff Hinton and his students' convolutional neural network algorithm that really dropped the error significantly. And since then, what we see now is the tremendous progress of deep learning and neural network-based algorithm. Many people consider the moment of that year's ImageNet Challenge the dawn of the deep learning revolution. And it's just exciting that as ImageNet Challenge continued, we see deeper and deeper network, bigger and bigger network and parameters and better and better performance of ImageNet recognition. So while that was all happening and exciting back in the lab, it was important for us to ask the question, what's beyond object recognition? Because those of you in human cognitive science know that there's far more things that humans can do visually than just recognizing individual objects. If two pictures have two objects, llama and person, a winning ImageNet algorithm would make them look like the same picture, but in fact, they might carry really different meanings. So the relationship between object matters. In fact, one of my favorite paper is a 2-page paper by Jeremy Wolf, who conjectured that in visual memory and perception, relationships between objects must be coded. And with that inspiration, we started to think about how to encode relationships of visual scenes between objects. And we created scene graph representation where the pink nodes are the anchor entities of objects, and the arrows you see are relationships between these pink nodes. Some relationships like verbs and predicates are in green, and some relationships like attributes are in blue here. So just to fast forward, we created a enormous data set called Visual Genome to push for algorithms to understand visual relationships, as well as language descriptions of visual scenes. And one example work by my students is visual relationship prediction work, or using scene graph, where we use a compositional model to piece together relationships in a scene. Our algorithm can recognize typical relationships like human riding a horse, human wearing a hat, but because of that compositional nature, it can also do zero-shot recognition of unusual relationships like horse wearing hat or a person sitting on fire hydrant. And we have quantitative results to show that kind of model is performed better than state of the art at the time of publication. And this scene graph representation actually had truly taken off. This is already old number from a couple of years ago. A lot of people from different areas of research have adopted scene graph representation for many different kind of tasks and algorithms. And we ourselves have taken it to videos to look at spatial temporal scene graph representation, and using that to do action and activity recognition and so on. And we even went a bit further in making computers to speak a story of a scene. So it's not just objects, it's not just relationships, it's actually a complete description of the story of a picture in sentences, like man riding a horse, horse-drawn carriage down the street, and so on. So that was a really fast summary of how we started with seeing is understanding, and started to work on important tasks like object recognition, visual relationship prediction, captioning, and so on. And if you look at the relationship between the real world and an AI agent, perception is the apparatus or the process of agent interpreting what the world is about. And within this domain, several ingredients are important. Representation is important. Learning algorithm is important. And data and benchmarks are important. And our lab has done more work in this that I'm just going to skip. But is that all? Is understanding all? We already said I had undergone a transformation myself, coming from computer vision field, that I was very happy doing understanding. But it really truly felt unsatisfactory at some point. I don't know how many of you have heard of Plato's analogy, Allegory of the cave. Describing vision could be a very frustrating process, as if, because our retina is projecting the 3D world onto a 2D surface, it's almost as if we're prisoners of the allegory of the cave, tied on the chairs. And even though there's a whole real life play happening in the back of our head, all we can see is the projection on the wall. And that's all we have to interpret the world. But if vision is that passive, there are going to be wrong things happening with that. For example, here's a very simple example to illustrate vision cannot be that passive, because if vision is completely passive, when we're presented with an object like this, depending on the viewpoint, we might have a very degenerate understanding of the world, which will render us incapable or incompetent to interact with it. In fact, we all know as animals, visual animals, that real visual experience is extremely dynamic and interactive. One of my favorite books in recent years is the book called The Other Minds. And here's a quote I like: "The original and fundamental function of the nervous system is to link perception with action." So there is a very profound linkage between vision, between seeing and doing. One last example coming out of developmental studies is this famous kitten study in the 60s. It's a little cruel, so I don't think it can pass IRB anymore these days. But the two kittens, newborn kittens, were put on the yoke. The active kitten is driving the yoke, hence moving the yoke. Whereas the passive kitten, who is not allowed to move the limbs and not much of the neck movement, gets to see the same world that active kitten sees, but couldn't move. And lo and behold, after a few weeks, the passive kitten has a damaged perceptual capability, whereas the active kitten developed a normal perceptual capability. This speaks of the importance of the interplay between moving, doing, and seeing. And of course, we've seen that we've discovered mirror neurons in primates where the link between doing and seeing is also extremely intriguing. So basically, what happens in evolution, in my opinion, and is that perception was driving interaction, and that interplay is driving the evolution of intelligence. So seeing is for doing in the world. That's what kept me very passionate in the past few years in terms of research, and inevitably it's bringing me to robotic world. Robotics is a pretty long, is a classic field for a while. And if you look at industry today, especially in highly programmed and structured environments, we are already using robots. But what is left unsolved and challenging is how to empower robots to do things in unstructured environment, just like intelligent animals do. And that's what I've been working on. And there are many topics in robotic learning connecting vision. That's really extremely exciting. I don't know how much I can get to today. I'll try to be really fast, probably skip a couple. So there are curiosity-driven robotic learning we call explorative learning. There are task goal-driven exploitative learning. Just like visual understanding, representation is really important. And these are all kind of various studies that my lab has done. But I also want to just foreshadow, there is a missing piece that I've observed in robotic research, and we're actively working on that. So just quickly, in some of our recent work in, let's say, curiosity-based learning, we've been working with collaborators on how to do learning to play. And the idea is that how do we build a AI system or embodied development system that is intrinsically motivated to interrogate the world and learn the world. And I'm going to skip the details, actually. Here's just the crux of the work is that we create an AI agent that has a world model network to predict the consequence of its action, and also a self-model network to predict the error of the world model. And then the learning is trying to empower the self-model to produce adversarial actions to the world model and learn through these interactions. And the result is that, if you look at the blue curve, which is our algorithm, throughout the course of learning, it does have that kind of qualitatively developmental trajectory of learning ego motion first, and the emergence of object attention, and the interest in one object learning, and the multi-object learning. And we show that the result of that is this agent does better than random policies. Okay, so that's just curiosity-based learning. We also do a lot of what we call traditional robotic learning, where important skill sets like grasping, rotating, opening doors, and so on. But these are relatively short-term, short horizon, punctual activities. What we're really going after is what we call long horizon task. In this case is cleaning up the tabletop and stacking the bowls and utensils. And in this particular work, my student Fei-Fei Li and I used a similar concept as a scene graph and modularized short-term punctual skills into this representation called neurotask programming, and use this modularized way of training robots. I'm just going to fast forward. And of course, there's some quantitatively better results from our algorithm. But in this case, we're able to show robots able to sort multiple objects. And also robots are able to actually deal with human destructive behavior. For example, in this case, you're going to see the experimenter destroying the stacking stacked block. And because of the neurotask programming representation, the robot is able to reassess the state and go back to its task. I'm going to skip another word here. That is another way. It's a generative model way of looking at performing long horizon tasks. But I think my time is limited. This is more towards models like GPT-3 and so on. So I'll just skip this part to get to the last piece of work I really want to share with you. Okay, so it actually has been years that my students and I are doing perceptually driven robotic learning, and it's been a lot of fun, and we're doing it both in simulation as well as in real robots. And there are just many papers looking at different kinds of algorithms, you know, especially deep RL-based algorithms and so on. But the one thing that has always bugged me a little bit in my own research are a couple of things. One is we alluded to the skill level task, or what we call short horizon goals, is a lot of the robotic tasks are very, very punctual, like lifting, placing, and all that. And this is fine because you have to start somewhere, and we're still, the field is making tremendous progress. But what even bothered me more with my own research is how small scale our experiments are. And there's no principled way of picking the task. Why is stacking color block better than arranging forks? You know, and it lacks standard metric. And almost all papers come from individual lab setup. And there are consequences to this, right? Like if you take a robot to real world, you get things like this. Even no matter how much you train a stacking color block, this real world robot can now stack a single box. And so our long distance dream, all of us, especially graduate students, is for robots to do all the chores for us. So how do we get to that dream? One page of inspiration we want to take is from the field of computer vision and NLP, is that large training environments and benchmark did drive the research of both NLP and computer vision in the past decade, brought us deep learning, and played a very important role. So this also goes back to what we think J.J. Gibson wants us to look at, is really think about the real world. Don't just look at the small laboratory setting. So what is the ecological approach to robotic learning? My lab start to turn out our attention to a very real world setting that matter to all of us, and that is household environments. Household environments are ecologically complex, dynamic, and uncertain, has large variabilities, are interactive and social, and inherently multitask. So as we speak, probably within weeks, because we've got very good reviews, so knock on wood, we're rolling out a benchmark called Behavior, benchmark for everyday household activities in virtual, interactive, and ecological environments of 1,000 human tasks. Here, what I'm showing you is the simulation of behavior world, where the robot is just tour guiding you and seeing, we've made this whole virtual world where you can do 1,000 tasks. And our goal is to make this behavior benchmark and simulation environment large scale and diverse, ecological in general, complex, and standardized evaluation. And how large are we talking about? As I said, 1,000 activities. We have 50 laser scanned large scale real world scenes across 8 types, from homes to schools to grocery to office, thousands of object models, and infinite ability to instantiate texture, lighting, and all this. And it's realistic and photorealistic. It allows for kinematic and dynamic states of objects, from wet, hot to, drawers open and all that. It allows for flexible and deformable materials, realistic fluids, thermal effects, and interactivity. So I'm going to just be really quick. One thing that actually mattered a lot to us is how do we select 1,000 activities? Back in ImageNet time, it was easy. There was a dictionary or dictionary plus called WordNet. But in robotic learning, it's actually important we recognize the societal impact of robotics, right? There is a lot of concerns about robots replacing people and replacing jobs and taking away human agency. These are true issues to consider. In the meantime, we also have issues like aging population, the declining ratio of caregivers to seniors, and the lack of good quality in aging. So how do we reconcile these? That was actually a big question on our mind when selecting our 1,000 tasks. And we started with recognizing we need to ask humans what they want. What do you prefer robots to do for you in a household setting? For example, cleaning the kitchen floor, or shoveling the snow, folding laundry, cooking breakfast, shopping for shoes, opening Christmas gifts. Just tell us. The way we ask people to tell us is first we go to government data sets to get all the household tasks humans do. And then we went to a user study to ask how much you would benefit if a robot did this for you. And then we try to, solicit human feedback. It turned out cleaning is something everybody hates. Nobody wants to clean after a wild party or clean a shower or clean your toilet. But in the meantime, you want to open your own Christmas gift. You want to throw your own darts. You want to mix your own baby cereals. And I can attest for that. It's important. And so we are able to rank thousands of tasks and select the first top 1,000 that humans want robots help. And I'm going to fast forward all this. And then for those of you in robotic research, you know that after that, we have to create a logical form language to define the initial state for the robot's planning, as well as the goal state. And this is a language we created for robotic learning called Bddl, Behavior Domain Description Language, inspired by PDDL for some of you who are in robotic research. And then even creating this BDDL, we have to get a lot of human as well as AI help, including GPT-3. So the punchline is, after all this, we put together behavior 1K or 1,000 activities, and this is another example of the kind of environments and tasks our robots are now able to do their learning in. And there are many, many different kinds of objects, thousands of objects, models in many different states. And the one last piece that's missing, which I'll just mention, but not dive deep, for those of you in robotic research, is actually a simulation environment, that the physics engine, the rendering, and all that. And it's really important. Simulation is actually very critical for today's AI research. It's fast training, it's transferable, it's safe, and it can give us a fair and reproducible benchmark if carefully done. And there has been a ton of great work in robotic simulation environments. I'm not going to be able to acknowledge all of these environments: Habitat, 3D World, Sapien, Virtual Home. They all have their strength in terms of enabling the kind of robotic movements. But the take-home message is that our behavior environment has a very comprehensive capability to capture important things like thermal effects, transition machines, lighting, fluids, deformability, transparency. And we scored photorealism with real humans, and our environment which is in collaboration with NVIDIA, so we call it Omni-Gibson, scores the highest in perceptual realism. And I'm gonna skip more. And now we're ready to use behavior to challenge our community. I just want to say the challenge has just started. We have used a classic popular end-to-end reinforcement learning algorithm called SAC, Soft Actor Critic algorithm, to look at how it performs in behavior. The short story is that if you give it magic action, it can do some planning for, say, grasping skills, but as soon as you relax SAC into a more realistic behavior environment, the orange line shows a degradation of its ability to perform, which is really showing us that behavior is very challenging, it's very diverse, and the current state-of-the-art algorithms in reinforcement learning are still lacking in its ability. And this is just another study to show generalization is really still an issue. And I'm gonna skip some further studies of evaluation, which tells us this is actually my favorite number, 0 performance, which is that if you give today's algorithm no privileged information, it doesn't perform in behavior. But as you start to give the algorithm more privileged information, it starts to do better. So we have a long way to go. And one last question in some of your mind, I'm going to skip this. Okay. Oh, yeah. One last question in some of your mind is, how do you close the gap between sim to real? This is behavior is a simulated environment, but eventually we want to take the robot to real world. So to start with, we have built an apartment and a real robot on your right in our Stanford department, and we are actively working on closing the sim to real gap. But there's still a long way to go, and you know, we have success stories here showing you the robot. This is our real apartment in our building. The robot is able to do some things like pick up bottles, and I hope it shows us putting it in the trash, navigate to the trash can, and so on. But I'll show you, it also fails a lot. Like here is a failure of navigation, and also a failure of grasping, and many other failures. So a long way to go. This is a quick introduction of something I'm very excited by in our most recent work is behavior. The website is a little outdated. As our paper gets accepted in a couple of weeks, we'll update it. And many students and PIs worked on this project together. And we do believe that there is so much excitement and work happening in the world of robotic learning, and hope behavior can help moving the world forward. In conclusion, I hope I have at least share with you my belief that vision is a cornerstone of intelligence. And in this research world of doing vision and visual robotic learning, we were working on representation, learning algorithms, planning and control, as well as data and benchmark. And we're continue to be inspired by this ecological approach of perception and robotic learning. And thank you so much. Should I stop sharing? Yeah. Should I stop sharing?
I think it's okay. There might be questions related to something you want to put up, so it's up to you. But thank you, fantastic talk. I don't see any questions in the chat just yet, but so maybe I'll start off with my question, and then see what bubbles up. So what I love about your work, Fei-Fei, and it's probably obvious coming from me, is how much you take the world of psychology and human neuroscience to inspire your work. And my question is actually, it's sort of related to this sim to real gap, but just in the vision world, because it seems to me, if we look at human behavior, even within the image understanding, we are much more robust than machines are. Even things that are sort of hard for the human to believe would be problematic, like just putting a little bit of noise, speckled noise can destroy these algorithms. And so I'm just wondering what you think about. I mean, you've pushed now into the robotic domain. Are you still interested in trying to solve some of these more tricky problems that are back in the vision domain?
Yeah, great question, Diane. We're still working on that together, right? You're right. But I also think the picture has become a lot more complex. When we say humans are more robust, humans are also, in many ways, not as robust. So in, for example, in discriminating categories, humans, in general, we recognize now fewer things than computers can. For example, the number of car types, it's just, I probably recognize 3. My kids can recognize probably 100, but computers are a lot better. But whereas what you said, the adversarial examples also show how brittle this is. I think it speaks of the brittleness of the architecture of the AI algorithms. It's going after these really, Diane, our algorithms are running on hundreds of GPUs to do what humans can do with 40 watts. We're using millions and millions of training examples to do what humans can do in few shots. So clearly, there's more to be done in terms of not only the robustness, but the nimbleness and the flexibility of learning. And there are exciting work. One line of exciting work is foundation models that's happening in the world of AI, where you train a giant model and then you allow for rapid, adaptable, transferable, quick learning. Does humans do that? I don't know. Maybe if you combine evolution's history, we are kind of a giant foundation models. That's one line. And another line is neurosymbolic. Can we not just dump all these pixels and do end-to-end learning, but also add more powerful representation? So there are many explorations, but good question.
Okay. Thank you. So there's a question in the chat, so I'll go to that before opening it up to the floor. Patty, did you want me to read that? Or I think I just will, unless she unmutes herself. So where do you see the role of affective computing and emotions in learning? For example, human learning experiences include feelings of pain or frustration, peer pressure, satisfaction, etc.
Great question. Honestly, I think we are, if you're thinking about more vision and robotics, I think we're very, very far. We are beginning to, in some research meetings, talking about theory of the other minds, but theory of the other mind or theory of mind is still right now focused on just understanding the intention and maybe planning perspective of the other agent rather than the actual empathetic understanding of emotions. In NLP, sentiment understanding through words is a little more, I wouldn't call it easier, but graspable. And there are research, which completely is not my expertise, that's in that. But affective computing, I know there are researchers, especially MIT Media Lab, I believe, are doing that. And also human robotic interaction is another fertile playground for affective computing. My very shallow way of saying this, answering this question is, I think it's absolutely important. It's just, I don't know I haven't worked in this and I don't have a good grasp on where we start yet, given how far we are from understanding other agents' emotions and intentions right now.
So yeah, I just want to clarify. Yeah, you have to send your message to me or one of the co-hosts. It doesn't just broadcast to everyone, so I'll read it. So we have another question from. Now we're getting a lot of them. Let me start first from Pan Zhao. For robotics learning involving vision, what is your opinion about end-to-end approach versus modular approach? For example, perception plus planning plus control.
Yeah, this is a debate in the robotic learning community, and of course, the modular approach is quite classic, and we've got really great work, like people like Leslie Quabbelin at MIT is doing that, and then we've got end-to-end approach like Sergey Levin and Peter Beal at Berkeley. I am not very religious, to be honest, on this. I probably, if you press me, I do think if you look at the the end goal is generalization, especially generalization in with even reasoning ability, counterfactual prediction, and all that. From that point of view, I do think some level of modularization and also even neurosymbolic representation or might help. It's hard for me to imagine it's all end-to-end. That's my guess right now. But I feel we're still in exploration mode. And one thing that really is bifurcating industry from academia is I'm really curious to see how far industry can take us on just the sheer brute force compute. And I feel ambivalent about it, meaning, there's something really exciting, but is that all there is a question. And that might also, help us to answer this question.
Okay, thanks. So we have a question from Roxanne. I think she'll unmute and ask it. It's a longer one.
Yes, hi Fei-Fei. Thank you for the talk. I very much enjoyed it and nice to see you again.
Yeah, hi.
My question is, when it comes to data representation, you believe that the map is not the territory, and I do agree with you. But in computational modeling of the world, we do need some sort of representation. So what theory of how people represent the world do you believe in and use in your research? And there is an entire spectrum of theories from realism to idealism and whatever other theories in between. And how much does this worldview constrains the computational systems modeling of the world? Thank you.
Roxanne, I have to confess, I don't think I can answer that question. I'm not that familiar with the theories you mentioned. And it inspires me to read more. I'm sorry, but I don't think I have a formed view on the different theories for this yet.
It's very interesting because you do talk about perception and action, right? So realism says that there is a world out there that exists independent of us that can be described based on features, which is pretty much what object recognition has used so far. But you also add human action or robot action in this case, which is more like going from both ends of the spectrum. So there is an object out there, but it's also our action toward the object that creates this intelligence.
Yeah, I mean, you're asking such an intelligent question and it's loaded, right? Back in the object recognition days, that there's almost a Platonic belief that there is an idealized model of objects. And we were, for a long time, that was a theory I have for objects, is there is a model and we're just approximating some probability distributions. In terms of the recent work in robotic learning, I don't think I have quite formed a theory there, but would love to get pointers on what I should read on that front.
Sure. Thank you.
Thank you.
So I have a quick question. I don't know if it's a quick answer. From Asher Mai, what do you think of the future of artificial general intelligence? Is it going to be possible in our lifetime?
Yeah, so I get this question a lot, especially when I meet with business people. And as an academic, honestly, I don't know what this word artificial general intelligence means. If you look at the history of AI, right, it started back in the, people say Turing was one of the first people asking the kind of question. So you combine Turing's dream and question with the Dartmouth workshop of, Marvin Minsky, John McCarthy. Everything as a field we've dreamed of since the very first days of AI was about, can we build machines and come up with computational theories that has the level of intelligence as humans, the perceptual cognitive level of intelligence. And then comes different AI winters, deep learning revolution, and then commercial world enter the scene, and suddenly AGI became a marketing word around 2016 and 2017. And that word literally came out of industry. And that word took media by a storm. And suddenly people are saying there's AGI versus AI. But as an AI scholar or researcher, I don't see there's a versus. I think the dream of AI as a field has always been that general cognitive, perceptual, and behavior ability of an intelligent agent. So that's really my very nerdy answer. Typically business people wouldn't like that answer.
Okay, thank you. So Alejandro, do you want to unmute yourself and ask your question?
Yeah, thanks, Dan. That was an awesome talk. Thank you, Fei-Fei. It's great to see you.
I know.
I love everything you're doing, although I have to admit that I couldn't follow exactly all the complexity of everything that you're doing. But one of the
Sorry,
things,
I was jamming so much in. Sorry.
one of the things that is clear, and from my perspective as an audience member, was an easy blind spot to detect, is that you're saying that it's important to understand the environment that you're, where the brain is embedded or your mind is embedded in the world around. Well, the one thing that humans have a ton of is other humans. We are a uniquely social species, and one of the things that we do is learn from others. We see others, and like parents show kids how to brush their teeth or pick up those plates and take them to the kitchen. So how much have you considered, or would there be any value in actually putting other robot agents inside your world that already know the solution to things, and see how quickly you can then other robots can learn from them? Understanding that these robots are also embedded by other intelligent, among other intelligent creatures.
Great question, Alejandro, and wonderful to hear from you. So first of all, I brushed so much under the rug. In fact, imitation learning from humans is a very big and active area of robotic learning. We have our own lab doing a lot of this, and a ton of labs doing that. So recognizing humans and other agents are in this picture is totally true and important. In fact, one thing that excites me of the behavior work is that we set it up so that we can have multi-agents in the behavior environment. It can be other robots, but we also have a VR system with the behavior environment where humans can act in behavior environment. They can demo tasks, and we imagine they can even interact with the robots. We've already got incredibly interesting feedback from, say, geriatricians thinking about how to help the aging population, and say, this is a great way to iterate on design, because, how do we know what elderlies want? And we can use this kind of technology. So it's a long way of saying you're so right. that other agents is key to all this. And as a field, I think we must continue working in this. And then it connects to the effective computing question. If you work with other agents, at some point you've got to have that empathetic ability to understand what they want, right?
Okay, we're getting after the hour. I'm going to read the last question. It's a little bit of a different one, more about sort of how kind of meta question on science. So the computational cost is increasing significantly for most computer vision tasks. And there are not many research institutions that can provide such a resource. And so what do you think about this particular problem?
Thank you so much, whoever asked this question. This is actually a increasing digital divide, or whatever we call it, that concerns me. So now I'm going to wear the hat, not as an individual researcher, but as the director of Stanford HAI, is that because of recognizing this digital divide and also its outsized impact in academia and public sector, as well as implications to, say, traditionally underserved scientific and educational communities, we actually lobbied a bill back in 2021. It's actually one of the last bills. It's in the last bill passed by the Trump administration, where we advocated for a national AI research cloud. And Biden and administration and Congress have taken that bill and formed a 12-person task force to, as we speak, put together a proposal to Congress to recommend the establishment of a national AI research resource. And I'm one of the 12 person on this team and working actively with White House and NSF on establishing a national cloud and data commons to precisely address this issue.
Great, thank you, Fei-Fei. And it apparently didn't make it into my feed, but I hear that Ted has a question, and as a co-sponsor of this, I thought we could end with Ted's question. If you want to just unmute yourself, because I haven't seen it in the feed. So you're not unmuted yet, Ted.
I don't think we can hear you. Oh.
Am I okay now?
Yes.
My question has to do, I've had a long-term interest in linguistics, and in particular in the roles of metaphor. And when I think about your work, I wonder how this complexity of language and the thought processes, which of course the language is expressive of, how does AI ever going to handle that? Because it's a very it's an individual thing. Well, it's a general question that I don't have any answers for, but I'd like to maybe send you a paper or two on this subject that I think might interest you.
Yeah. So Ted, have you heard of GPT-3?
Of what?
GPT-3.
No.
Okay. So I'm happy to send, or Diane, send you the link. It's incredible how much AI language models have advanced in the past couple of years. GPT-3 is the latest language model by OpenAI, where it literally can do human level language tasks in an incredible way. And a lot of the students, especially here, probably use that. And literally last week, I talked to GPT-3 and asked it to write an essay using the same command that my fifth grader's teacher asked the fifth grader to write. And it just turned out a 4,000 character essay that is, I cannot tell it was written by a machine. And it was an essay on the pros and cons of electric cars. And so it wasn't like a prize-winning essay, I would say that, but it's incredible, the research progress on language models these days.
I look forward to seeing that.
Yeah.
Okay, well, thank you. We're over time. It was such a great talk. So I just want to thank Fei-Fei again for her fabulous talk.
Thank you, everyone. So great to be back. Yeah,
And
bye.
thank you all for being here.
Yeah, bye.
Bye.